Good day, everyone. The title of my presentation is Ocean Acidification Wreaks Havoc on Marine Life. Thesis Statement: the ocean absorbs a significant portion of carbon dioxide emissions from human activities, equivalent to about one-third of the total emissions for the past 200 years from fossil fuel combustion, cement production, and land use change. Uptake of carbon dioxide by the ocean benefits society by moderating the rate of climate change, but also causes unprecedented changes to ocean chemistry, decreasing the pH of the water and leading to a suite of chemical changes collectively known as ocean acidification. Like climate change, ocean acidification is a growing global problem that will intensify with continued carbon dioxide emissions and has the potential to change marine ecosystems and affect benefits to society. What is ocean acidification? When carbon dioxide enters the ocean, it dissolves in salt water. First, it forms a carbonic acid. Then this carbonic acid breaks apart or dissociates, producing bicarbonate ions and hydrogen ions. Ocean acidification results from an increased concentration of hydrogen ions and a reduction in carbonate ions due to the absorption of increased amounts of carbon dioxide. Clams, mussels, crabs, corals, and other sea life rely on carbonate ions to grow their shells and thrive. Okay, this is the processes of ocean acidification. So atmospheric carbon dioxide will enter into the sea, then the seawater will dissolve the carbon dioxide. So there is now the mixture of carbon dioxide and seawater. So once it will mix together, it will form or produce carbonic acid. So this carbonic acid will dissociate or split apart, and it will produce bicarbonate ions. Due to the increased concentration of carbon dioxide, so less of that will dissociate to form carbonate ions, because this carbonate ions is very important for calcification of the marine life, especially the shells. So because there is a less process of calcification, so some of the shells are deformed. And there is also the uh, increased level of hydrogen ions that will make the seawater acidic. So because when there is the dissociation of bicarbonate, so some of the hydrogen ions will be released, so the seawater will become acidic. Carbon dioxide concentrations drive rising temperature and acidification. The rising concentration of carbon dioxide in the atmosphere is driving up ocean surface temperatures and causing ocean acidification. Although warming and acidification are different phenomena, they interact to the detriment of marine ecosystems. These changes to the ocean aren't occurring at the same rates everywhere. There are significant differences across gradients of temperature, latitude, and depth. Carbon dioxide concentration will cause rising of global temperature. So as the years progresses, so the carbon dioxide concentration will also increase. At the same time, there's an increase in global temperature. So, in other words, it is directly proportional. So the rising of global temperature is directly proportional to the carbon dioxide concentration. Ocean acidification affects the economy, people's livelihoods, and communities. Shellfish fisheries are also feeling the impacts of carbon pollution. In places like the Pacific coast of the United States, warming waters and ocean acidification are expected to reduce the Dungeness crab population, the highest revenue fishery in Oregon and Washington. Fisheries in the Northwest are already feeling the impacts of warming waters, which are wreaking havoc in the region and causing multi-million-dollar losses to local economies. Warming ocean temperature have caused a rapid increase of toxic algal blooms. Toxic algae produce domoic acid, a dangerous neurotoxin that builds up in the bodies of shellfish, posing a risk to human health. Dead corals litter a beach in Bolinao, Philippines. Global warming, which causes ocean acidification and contributes to coral bleaching, is compounding the threats posed by destructive fishing techniques, coastal development, forest destruction, and aquaculture. These stresses are putting hundreds of corals and fish species and millions of people dependent on Filipino reefs at rest. Ocean acidification affects the habitat of marine life. Philippines seawater problems. So the problems in the Philippine seawater it is because of massive throwing of trash in the sea, especially uh, people who are settled near the sea. Current scenarios for carbon dioxide emission could make the ocean up to 150% more acidic by 2100s. Many ocean plants and animals build shells and skeletons out of two chemicals that exist in seawater, calcium and carbonate. Thus, increasing acidity will make it harder for corals to build skeletons and for shellfish to build the shells they need for protection. Increased acidity slows the growth of calcium carbonate structure and under severe conditions can solve the structures faster than they form. Okay, let's watch the video on ocean acidification.
Hi, it's Paul Anderson. I'm sure you're familiar with global warming, how increases in the amount of carbon dioxide is warming the planet, but you may not be familiar with global warming's evil twin, ocean acidification. The cause is the same, increases in the amount of carbon dioxide, but the mechanism is different. Let me show you a demonstration. This is regular distilled water, and I'm going to use a pH meter to measure the pH of regular H2O, and it's going to be right around 7. Now I'm going to take that same distilled water, we're going to put it in a bottle, and we're going to add carbon dioxide to it. We're using a SodaStream machine to shoot carbon dioxide in it. It's now just carbonated water. We're going to put it in a glass, and we're going to measure the pH now. I want you to make a prediction of what you think the pH might be. You could even use your finger and point on the screen to where the pH scale is going to be. Let's see how you did. The pH is going to be 3.6. It's really acidic. Let me show you what's going on. So if we take carbon dioxide and water and mix them together, we get carbonic acid. Now that can quickly dissociate and form bicarbonate. What we're doing here is we're losing one of these hydrogen ions, and that can dissociate again and we can form carbonate. We're losing two of these hydrogen ions. Now if we look at the definition for what pH is, pH, remember, is the negative log of the hydrogen ion concentration. What does that mean? The more of this H plus that we have in solution, the lower the pH is going to be, and it's going to be more acidic. If we add more carbon dioxide, more of it's going to move in, and we're going to have more of this hydrogen ion, and we're going to have a lower pH. Now, the levels of each of these can change. Each of these are reversible reactions, so depending on the amount of carbon dioxide, it can move towards the left or it can move towards the right. Why is this a big deal? Well, life exists in this water, and life is regulated by proteins, and proteins require a specific pH. So studies are showing that if we decrease the pH and make it more acidic, organisms are having a decrease in metabolism, and they can have a decrease in their immune response as well. Now, how much of a change in pH are we seeing? If we look at pre-industrial levels, the pH of the oceans was really basic, 8.25. Post-industrialization, it had changed to 8.14. Now, there are going to be regional differences you can see on this map right here. And you might say that's not much of a change in pH, 0.11, but remember this is a log scale. So that represents a 30% change in the pH. What's it going to look like in the future? Well, as we play those models out into the future, by 2100 it could be as low as 7.80. Now, this low pH is going to devastate ecosystems for a different reason. This last carbon compound of the three is carbonate. That combines with calcium to form calcium carbonate. That's what the shell is made up of. That's what the bulk of a coral reef is made up of. And as we change the pH, we can change the level of that carbonate. What determines the concentration of these three? Well, it's going to be the temperature of the ocean water, the alkalinity, but also the pH. And so we can use a Jerome plot to figure out what's going to happen over time. These are log scales of the concentration of these three compounds. The green represents the amount of carbonic acid, the red line represents the amount of bicarbonate, and then the black line represents the amount of carbonate. Remember, that's important for shells. And so if we look at it at acidic levels, carbonic acid is going to dominate. At neutral levels, bicarbonate is going to dominate. And then at basic levels, those that we would find in the ocean, carbonate is going to dominate. But this blue area represents what's going to happen as we change the pH. And as we decrease the pH, you can see what's going on. The carbonate levels are going to drop off, and the bicarbonate levels are going to increase. That's because that free hydrogen is competing with the shellfish, really. The free hydrogen is competing with that calcium carbonate to form more bicarbonate. And so now shells can't make their shells. If we look at what could happen over time, this is a pteropod shell at 7.8 pH. It is literally going to dissolve. And so if we look at, for example, coral reefs, they're getting hit with a double whammy. We've got global warming. An increase in the temperature is going to cause them to bleach or kick out all of their algae. I'll talk about that in a different video. But this ocean acidification is going to take that carbonate, and so they can literally not build more of the coral reef. And so these two things work together. What's the good part of global warming and ocean acidification? If there is a silver lining, it's that they both have the same cause. It's increases in the amount of carbon dioxide. If we can decrease the amount of carbon dioxide, we can cool off our planet, and we can also slow down this ocean acidification. I wanted to thank Rebecca Blake. She put this out as an idea of a video.
When carbon dioxide is released by humans, around 30 to 40% is taken up by the oceans. The rest either remains in the atmosphere or is absorbed by the land. This causes oceans, which are alkaline, to become more acidic over time. Since the start of the industrial era, the overall pH of the world's oceans has fallen from 8.2 to 8.1. As oceans become more acidic, the number of hydrogen ions in seawater increases. Some types of coral have a hard outer skeleton made out of a compound called calcium carbonate. This compound is made of calcium ions and carbonate ions. Ocean acidification causes the amount of calcium carbonate in seawater to fall. This is because some of the carbonate ions that normally pair with calcium to form calcium carbonate instead pair with hydrogen to form bicarbonate. With less calcium carbonate around, corals find it more difficult to rebuild and grow their skeletons. This increases the chances of coral death.
Okay, so planting seagrasses to reduce ocean acidification efficient at sucking up carbon that they cycle through roughly the same amount of carbon every day as all the land-based plants. Kelp is also well known for soaking up excess nutrients and making waters cleaner for shellfish. Oyster in estuary that once had a thriving industry host an effort to put old shells back into the water, thus adding calcium carbonate into the water. Using rocks to buffer ocean water, for example, involves using energy to treat the minerals beforehand so they dissolve, and then there are toxic levels of nickel or cadmium hitching a ride along with the rocks. So these are the cause and effect of ocean acidification. So my conclusion, ocean acidification impacts important sectors in economy like fisheries and tourism. It affects food supply and makes global warming worse by hindering the ocean's ability to absorb carbon dioxide. For communities that depend on coastal resources, their way of life and cultural identity are on the line. If carbon dioxide emissions continue unabated by the end of the century, ocean acidification is expected to reduce harvest of marine life. The most effective way to limit ocean acidification is to act on climate change, implementing solutions to dramatically reduce the use of fossil fuel. If we dramatically cut our global warming emissions and we limit future warming, we can significantly reduce the harm to marine ecosystem. Thank you for listening. I am Marichu Hanamham, your presenter.